Well, what a fantastic beginning to the day two of the RailTrans Expo 2025. With this, we are now headed towards technical presentations. To talk about Infineon Technologies, Power Solution IGBT SIC for India's future mobility. Joining us on stage is the Senior Principal Engineer, Industrial and Consumer Power at Infineon Technologies. Please put your hands together for Dr. Kwok Wai Ma.
Thank you for the introduction and thank you for joining this section. I'm very happy to have the financing section before a technical section because for two reasons. Technology always needs finance, okay? No money, no technology. So therefore, it's good that the concept of finance is put before so that people understand why we need more money to invest in the finance. And second point is also important is technology bring back revenue. The revenue that technology bring back should also be recognized in the finance model. So therefore also count it into the total cost calculation. So that is a kind of opening. Okay. So today my topic is talking about next generation of power semiconductor driving next generation of train. Okay. So I'm going to explain next generation of power semiconductor in railway. I'm coming from Infineon. So probably you may not heard about the name Infineon, which is very understandable. And probably you may also not understand why we talk about semiconductor in train. Okay, so some simple and important explanation. Infineon is the one of the biggest semiconductor manufacturer in Europe. So we are based in Germany. Our headquarters is in Munich, but we are very global. So we have office, sales office, technical lab, manufacturing location all over the world. And in India, we have office in Bangalore, Delhi, and Pune. So we are doing all the different type of semiconductors covering safety and security, industrial, power, and automotive. So my division is working on power semiconductor. And actually, Infineon is the biggest power semiconductor manufacturer in the world. So why we talk about power semiconductor in this context? The reason is also very simple. Nowadays, in a modern society, everything works with power. It starts from your mobile phone, with your computer, and at your home with the air conditioner, with your washing machine. And when you go out, you drive an electric vehicle, and you need electrical vehicle charging. And we talk about renewable energy that come from the wind turbine, as we hear the presentation yesterday. And we also talk about power transmission. So all these are power. And to control this power that can change from megawatt to gigawatt, you need power semiconductor. So that is the background for today's presentation. And today, most of the semiconductor is made of silicon. So silicon is the basis for the semiconductor today, including power semiconductor. But there is a big revolution in power semiconductor technology that is underway, what we call wide bandgap power semiconductor. This is completely changing the game by using very unique material which offers very surprisingly good behavior that allow us to make power semiconductor that can switch faster with lower loss and higher blocking capability. And that is the basis for the use of such semiconductor into railway application. So before the PowerPoint, I can also briefly explain. So the key benefit of power semiconductor is switching. So we switch to control power. Thank you. Okay, finally it comes. So we're just at the right point. Okay, so this is how power semiconductor is used in every part of the application. So you see consumer application like phones or computer, You see industrial applications like motor drive, electric vehicle, and then renewable energy. And then you see always we have a trade-off between power and frequency. So the faster you switch, the lower power. And train, railway is a very high power application. So therefore you see on the top left corner, you see the railway's logo here. The use of wide bandgap device allow us to switch much faster, nearly 10 times faster than today. And that is the motivation why we want to use silicon carbide device in railway application. The benefit that can bring from silicon carbide device is it can switch faster with lower loss. So therefore, we can use this device to make converter which is smaller and lighter. We can also use this benefit to drive higher power. It all depends on the design of the train. So this is showing the functional block diagram in a train propulsion system where you have the input circuit that take either AC power or DC power from the catenary, and then you have the transformer or filter circuit, and then with a rectifier. On the output side, you have the motor circuit, which with inverter to drive the PMSM motor in the bogie. And in certain multi-systems, you may have DC or using battery to drive the train, so you may have a hybrid circuit. In all this system, when we using silicon carbide device, you can generate the benefit of lower switching loss, lighter and smaller converter, and lower noise. So therefore, this benefit will be reflected into the train's performance and comfort. So the use of silicon carbide device is already being understood by many of the traction company and also railway operator. So the question is just to prove it, to demonstrate. So therefore, you can already find many reports from different company to test one trains, different type of train using silicon carbide. So for example, a few years ago, Siemens have joined with Infineon to use 3.3 kilowatt silicon carbide module in a tram in Munich. They trial one for 1 year, and then the operational manager concluded that it saved them about 10% electricity and also give very good passenger experience of much quieter operation of the train. And meanwhile, they're also trying silicon carbide on their hydrogen train, which is also demonstrating the benefit of high efficiency, lower weight, and also simplified cooling system design. And also in Sweden, Bombardier has also tried silicon carbide in their metro subway, and they quantify even the benefits of efficiency, weight, and size. I think the last example is of the most important reason to India. Talk about the high-speed train project from Bombay to Ahmedabad. The Shinkansen train is also reported their test results using silicon carbide device. Again, the common benefit of lower weight, higher power density, and also more efficient cooling system design was understood. Okay, so this device characteristic of power semiconductor is translated into tangible benefit to a railway propulsion system. For example, you see the inverter designed using silicon carbide device is typically 20% smaller than the traditional IGBT-based design. The higher switching frequency allow either higher output power, lower power loss, or smaller system design. And the low loss also bring in additional benefit of user comfort because you need less cooling effort. For example, smaller fan, and also there's less vibration in the motor and the converter. So therefore, the noise, the audible noise in the train compartment will also be lower. So therefore, this is of particular importance for passenger train or metro subway. So we can quantify this benefit because you see on the right hand side, you have the frequency axis in the x-axis and the power on the vertical axis. So the use of silicon carbide device allow both higher switching frequency and higher output power. So we can then map this into the design of a propulsion converter as an area for improvement. So that means you can use this benefit provided by silicon carbide device to improve either your system or your propulsion system power. So how to translate it? Because different railway or different railway application or even different railway operator and customer, they have different preference or different status. So therefore, all this benefit can capture the different voice or expectation of customer. So you will often have some conservative customer that, I don't want to change. My system is very good. So I can try to plug and play the new device to see what happens. So which is the number two here. Even you don't do anything, you are number two. You are very conservative. You don't make any change. By changing from silicon device to silicon carbide device, you already gain. You gain in energy. You gain in power. You gain in operation costs because of the energy saving by silicon carbide. Okay, if you are performance driven, so for example, if you want to develop a locomotive that can drive even more heavy load, then you can go for higher output current, which is the number 3. Okay, you can deliver the same train with higher power using silicon carbide, or you want to deliver the highest performance in the train by packing more devices together. Then you switch at higher switching frequency, put them more in parallel, and then you deliver the higher power at the smaller size. So all the different expectations can be put into this triangle of improvement. Okay. So while I have been talked a lot about, while I've been talked about a lot on performance, one thing that is always most important in railway application is reliability. So, sorry. Yes, okay. So one thing that is very important is reliability. So I think if you participate the presentation yesterday, you will listen to one of our speaker telling that the total cost of running a railway system, 50% is maintenance. So this is very, very important because a train will run for 20 to 30 years. Along the way, any disruption on operation will cause maintenance costs. So therefore, lifetime and reliability is critically important in railway application. And reliability is not by chance. You have very strict science and technology behind to achieve high reliability. So let's start from the very beginning. Start from a chip. The chip on the top bottom is the basic unit of a power semiconductor that do switching. The failure rate requirement is extremely low. We are talking about few failure per billion hour. Billion, 10 to minus 9. Okay. You may wonder why we need such a high reliability. Okay, then we do the step up. We can't make a device by just one chip. We need many chips together to make a module. So for example, in the second column, which is typically a IHV module used in the locomotive or in the metro subway. In such module, you have 36 chips. So therefore, the failure rate will be roughly 100 fit. That means 100 failure per billion hour, which translates into thousands of years, again, which is very long, or regarding MTBF. But you need many of these modules to construct traction converter. So typically 14 to 20. So that means then the MTBF, mean time between failure of a traction converter, is in the range of hundreds years. And for a EMU, like high-speed train, you have 16 or 8 sections. Then you need one traction converter for each EMU. So therefore, the MTBF is about 15 years. So, and for an operator like the Delhi Metro or Bangalore Metro or the National Indian Railway, where you're running hundreds or even thousands of trains, you need this type of MTBF for 15 years of the train to have a maintenance period of, say, few months or few period. So therefore, you really need a very, very high reliability for the power semiconductor to control and minimize your maintenance costs. So how to achieve reliability? Okay. So as I say, reliability is a subject which is very difficult to demonstrate and also to develop because it takes long time. So here I show you one example which is from my customer in Korea. About 10 years ago, they come to me, they want to understand the field reliability, field health of the power device for the passenger train running in Korea. So therefore, they take out one of the working train, take out the power semiconductor module, send to Infineon for analysis. They want to know how healthy is this module. So therefore, we perform the same analysis, just like a failure module. So therefore, you see in the right-hand side, we cut away the module, checking all the mechanical construction, and we go deeper in checking the solder joint contact, and we use ultrasound microscopy to check the solder joint connection, which I show in the middle and the right-hand side. So maybe you can already see that there's some small cracking, which I show as a pointer. That is the worst part of it. So therefore, we see some small cracking. And on the right-hand side, you see the base plate, which is perfectly okay. So if I use a general statement, I would say the age of this device is still a teenager after working 10 years in field. So this example demonstrates what a highly reliable semiconductor module should look like for railway application. Okay. So how to achieve this? Okay. So to achieve this high reliability, you need packaging technology. And especially when we are moving to the next generation of power semiconductor using silicon carbide, you need a new technology to achieve an even higher level of lifetime and reliability. The packaging technology that Infineon developed is called .xt, which is using copper. So copper is a very rare packaging technique used in semiconductor, and copper can allow the highest conductivity and also the strongest bonding. We all use sintering instead of soldering to connect the chip to the substrate, because sintering can create the strongest bonding between the silicon carbide chip to the substrate. So with all this technique, we are able to achieve a power cycling lifetime 10 times higher than before. So according to the normal operation, we can foresee that this module can operate 40 years in field. Another example illustrating the importance of knowledge in reliability is, because silicon carbide is a new technology, that some of the failure mode is different from silicon. So Infineon identifies such failure mode, and we publish our knowledge in scientific paper. And at the same time, we also publish application notes telling our customer how to design the power device such that you can minimize such failure. And at the same time, we push this knowledge into the standardization organization to put this as a standard way to test and qualify silicon carbide devices. So therefore, on the right-hand side, you see the latest standard published by JEDEC, By the way, JEDEC is the international standard organization for semiconductor reliability. So the JEDEC standard is using Infineon approach to test and qualify the aging of the gate by the same testing method. So the key message of my talk today is silicon carbide device is a new and revolutionary technology that can switch much faster than the silicon power device today. And by that, it can reduce the energy loss, increase the switching frequency to reduce the size and the weight, and also reduce audible noise. And the designer can take advantage of all this benefit to fit the application. And the use of dot XC technology with copper metallization and sintering will increase the lifetime to 40 years. Thank you for your attention.
Thank you for quenching our thirst and adding to our pool of knowledge. With the same, requesting Mr. Surya Shah, Executive Director at Urban Infra Group, to kindly join us on the stage to present a small token of appreciation on our behalf. Also requesting the entire team to kindly join us on the stage for this special moment. और वो हिंदी में कहते हैं कि तालियों पर जीएसटी नहीं लगता, तालियां टैक्स फ्री हैं, तो ज़रा दिल खोल कर बजाएं. That was Dr. Kwok Wai Ma, Senior Principal Engineer, Industrial and Consumer Power at Infineon Technologies.
wonderful idea and very thoughtful and a great exhibition. I really congratulate not only for organizing this thing.
यहाँ पे आने के बाद मतलब 2 दिन हमने स्पेंड किया और 2 दिन में हमें काफ़ी सारे अच्छे क्लाइंट्स मिले। इवन सम हमें रेलवे की भी कुछ ऑफिसर्स मिले।
When we had installed our stall, we were getting all the supports, all the manpower, all the equipments and tools that we needed. It was really pleasant experience over here.